So that was the first step of docking, generating lots of confirmations. And at that point, generate anything. You don't have to know whether it's good or bad, just generate it. The second phase, though, is scoring. Now I need to say, given all those confirmation, which ones are good and which ones are bad. There is more than one way to skin this cat, too. There are three common ones. We could do something that is force field based. Remember the force field in the molecular dynamics simulation? This is pretty much exactly the same thing. We try to calculate all the interactions between atoms. This might be accurate. We have to do it a bit more sloppily here because I don't have the water, so I have to represent the water indirectly with, say, with the surface I'm exposing to water and whether my atoms are hydrophobic or hydrophilic. This can be a bit costly, but it's frequently pretty accurate. So at least for the atoms closest between the receptor and the ligand, we normally do that. We can add empirical terms, though. For instance, hydrogen bonds. Do you see the difference here? In molecular dynamics simulations, we relied on detailed balance sampling according to the Boltzmann distribution. Then it was very picky that we had a proper potential and calculated forces and generated new conformations according to the Boltzmann distribution. Here, I couldn't care less. If we know that it's usually good to have hydrogen bonds, so if you have many hydrogen bonds, awesome. Let's just count the number of hydrogen bonds. And if the molecule conformation I'm testing here has lots of hydrogen bonds, add that to column 2. If column 2 has a high value, you should keep that molecule. The third option is what we call knowledge-based. Or statistical scoring. You actually know this. This is pretty much Boltzmann inversion. So if we look at the protein data bank and all the proteins, and we know that if I have a ligand bound, it's very common that the distance between, say, the aromatic ring and an oxygen is 3 angstroms. If we have enough statistics like that, you can calculate the probability for that, right? And if we have the probability, we can turn that into potential. Delta G equals minus RT ln, the quotient of the probabilities. So knowledge-based scoring really just means that look at statistics of known structures, known complexes, and when I see patterns that fit that, I should score them high. We could decide to use kilocalories per mole for our scores, but really I can use anything I want. I could introduce the Lindahl score, that is a number that should be high. All we care about here is that can I find a way to separate things that are likely to be good binders from things that are likely to be bad binders. Do you notice one thing here? I'm only predicting binding. That's really the only thing we can do with docking. So here I need to rely and hope for that high affinity is going to be the same as high efficacy, which is usually the case, but it's not a guarantee.